Welcome back. So in this section, we are going to continue our discussion about operation in binary search tree. Okay? In our last lecture, we discussed search and insert. Another important operation in a data structure is a delete operation. So let's take a look. And because it's a tree structure, okay, so the delete operation, we need to consider multiple different scenarios. Okay. The first is if the tree has only one node, and definitely that node is going to be the root node. Is it? If it is a root node, if you delete it, the tree basically is gone. Is it? So then in this case, don't forget to reset the root node to null so that you know the tree is empty there. Okay, the second case is the item you are going to delete is at the root node. Okay, so then if this is the case, we need to do some rearrangement. Later on, we will see, okay? And then at the same time, you need to update the root node after the delete operation. So also this is very important. So that's the second scenario. Then the third scenario is the item at the leaf node. Okay, so suppose you have something as it 59, and then here you have 58, suppose. Okay, and you try to delete this 58. Then just remember this 59th left subtree, you need to reset it to null. Is it? So you identify then this node is going to be so this node, so the parent node basically of the node. So this is a leaf node. Then this is a parent node. Then just to remember, okay, the parent node's left, then you need to set it to null. So similar, this is suppose here is 60. And if you want deleted, then you need to set parent's right to null. Okay, so we needed to do this for the leaf node case. And there are some other cases, item with a single child. Okay, so a node you're going to delete just have one branch. Okay, one branch doesn't, the other part is null. Okay, so the single child branch. Then we needed to determine whether the node is left a child of the parent. Okay, and then what you're going to do, you replace the node with the parents. So you try to delete this one, is it? And then with its parent, is it? So you're going to reset. Okay, so noting that with the node single child, is it? So you reconnect its parent node to the child branch. Okay, so that's the single child case. Then the most complicated is the item with two children. Okay, with two. Then how are we going to? We cannot do this single child case. Is it? Then we first need to do some swap operations. So swap the item with its next in-order successor. Okay, so this in-order successor concept. So keep that in mind. What that means? That means the next item in ascending order. Okay, so that means we need to follow that in-order traversing, is it, to find it. Okay. So the next item in the ascending order. So then the problem can be reduced to either the leaf child case or single child case. So reduced to either one of it, then we can go ahead and use the approach, the respective approach. Okay, so that's the general scenarios for delete operation. Okay. So next, let's take a look at an example to better understand it. Okay, so let's take a look. So for this tree, okay, First, let's see, we delete 36. So you first need to find search 36. We need to search first. Okay, so 36 less than 55, go to left. Compare with 50 less than, compare with 28 greater than, compare with 39 less than, compare with 35 greater than. Then we find it. Is it? Will you find this item? Okay, so this is a parent, this is a cursor. Is it? So you set parents right, basically. Into then this 36 is gone. Okay, so that's how we remove 36. So this is a very simple case. This is just the leaf node. That's the leaf node case. And then this is leaf node. Then let's take a look, 39. So we first need to compare. I said 39 less than, go to left. Less than, go to left. Compare with 28 greater than. Okay, so we find 39. But it's not lift, it's a so for this lift, for this 39, then you check, okay, the right subtree is null. So this is the case of single child node case. Okay, single child node case. So because we want to delete it, so we during our search we keep track of the parent node. So this is a cursor. You're going to delete it, is it? And here is cursor's left. That's the left subtree, is it? What we want to do is we want to, you're going to delete this. So you're going to reconnect the parent right to this cursor. So what you can do is parents right and set to cursor's left. Okay, so now this item is gone. So you have the new tree, okay, new branch, and it's still satisfy the binary search tree ordering rule, okay. Okay, and then next, let's take a look. Take a look, the last item we want to delete is 65. So same thing, we do search first. We compare with 55 is greater than. So we move to the right. Yeah, and we find it. Is it? And this node has two nodes. It has two nodes. For the two nodes, what it needs to do is you cannot like just reconnect. Is it like the single, like a 39 case? We cannot do that. It's also not a leaf node. We cannot do. So we need to find a way. So the idea is you first need to find its next in order successor. The next is the ascending order. So it is this one. Is it how to find it? You go to its right and then move to its left, all the way. Is it? Okay, then we can find, okay, 69 is its next in order successor. Okay. And after you find it, we are going to swap the item. Okay, so you swap 69 to 65 location and put 65 to 69. Okay, and after that, if you take a look, the case then is going to be, you're going to remove 65. So swap, then remove 65. Now this reduced to the case reduced to single child case. Is it? So yeah, for a node that has two left and right has two child nodes, then the case you first need to find its next in order successor. How to find it? Go to right first if the right subtree exists, and then for the right subtree, then you follow the left all the way, okay? And then you identify that node. That node will be either the leaf node or a node with a single child. That then the case reduced to either the single child node case or leaf node case. And then we can just using one of this option to do it. Okay, so that's the case for a node with two child nodes. Okay, it's a little bit of more complicated. And then remember, like in this case, if you want to remove 55, okay, that's a root node. Then similar, you first need to find its next in order item, is it? And then do swap, and then do the remove. Okay, so that's the regarding our delete operation, okay, in binary search tree. So just be careful. There are different scenarios you need to take care of, okay. So in our implementation, we will see that. Okay, and if you recall previously for our traversing, like the in order, pre-order, post-order, okay, those traversing is using recursive traversal. Okay, and they go to the left subtree as far as possible, or go to the right subtree as far as possible, is it? So those we call it depth first search. Okay, and here we are going to have another concept. It's breadth first search. Okay, so breadth first traversal. So how do we do that? Basically, it's also we call it level order traversal. So we are going to traverse the node level by level, starting from the root node. Okay, so this is a binary search tree. Okay, so for each level, so we can describe the level. So root is level 1, and then the two child nodes of root node, we call it level 2. And the nodes of the grandchildren of the root node, we call it level 3. And the great grandchildren node of root node, then we call it level 4, as it can going on. Okay. So the case is here, you're going to do level by level. So you do G first, then F, and then J, then B, I, P, then C. Okay. So you do level by level. Okay. So then the question how we are going to do that, is it? So so definitely, clearly we can see this is breadth first. So it's go as wide as possible, is it, at each level. Only after it complete the level, it will move to the next level. Okay. So then the question is, how do you do that? Is it? And for the depth first, we use recursive, is it? So here, the way to do the depth for to do the breadth first search is we can use a data structure called queue. We can use a queue, okay? So here is that queue. So initially we start with a root node G, okay? So G is in the queue, okay? When G is in the queue, okay, then we get a G out, output G. But we need to put its two child node into the queue, okay? So left first. So then F, then J first, okay? Now in this queue, okay, we need to empty out this queue and empty out these two nodes. Okay, so F, you empty out, but you need to get its nodes to the queue. Okay, so it's B. So each time when you remove an item from the queue, you need to add all of the child nodes of that node to the queue. Okay, and then we come to node J. Okay, so node J output, but we need to add its two child node into the queue. Okay, so node J is out. And then we come to node B. Okay, we want to output node B, but we need to get its child node to the queue. Okay, so C is in the queue. And then we come to node I. Okay, node I is out from the queue, and node I doesn't have any child node. So we don't need it. We don't have anything to add to the queue. And then come to P, okay? So node P is out, and node P doesn't have any child node, so no new item added to the queue. And then come to C. Node C is out, and node C is a leaf node. So there is no, so empty, is it? No new item added to the queue. So now the queue is empty, so your traversing is also terminated. Okay. So then we can see the output is level by level. Is it? It's G, and then FJ, then BIP, and then C. Yeah. So this we call it so breadth first traversal. Okay, breadth first traversal needed to take advantage of the queue structure. Okay, so that's regarding breadth first traversal. So we discussed depth first traversal and breadth first traversal. Okay, and we already discussed the steps for the depth first, breadth first traversal. Okay, so now let's take a quiz. Okay, you can try to answer it after you watch this video. So it's still the true-false quiz. Okay, and the first question is. Says a node's next in order successor who will be in the next in order successor. It said locates node's left subtree and rightmost node on the left sub-branch. So is it true or false? And also in binary search traversal, it says recursive traversal is depth first, while level by level traversal is breadth first. So is it true or false? If it is false, why? Okay. Okay, so that's the discussion for this section. We'll come back to discuss the next section in a little while. See you.